Cool. Dr. Marcel Atemkeng is a researcher with more than 5 years experience in high bandwidth signal processing. Data science with a strong background in applied mathematics and computer science, artificial intelligence, and radio interferometric data processing. He's currently developing novel dimensional reduction algorithms and applying deep learning techniques for the SKA big data. Marcel is also a lecturer in machine learning or deep learning and the coordinator of the AI research group at Rhodes University, where he's supervising a number of students. And then you can also get the link to his work on our blog on there. So Marcel, welcome, and you can take it from here. You just switch on your camera and you can start presenting.
Thank you very much. Let me share my screen. Okay, thank you very much, Kosi, for inviting me to this Data Science Society seminar. The talk today will be based on the approximation theory of convolutional filter in the map of a radio telescope. So, well, the approximation is quite very mathematical, but I try to simplify it as possible. You know, and also I'll use this as opportunity also to present to the audience, because I'm quite sure most of the audience, they are new to the field. So I'll use the opportunity to show how what is a radio interferometer and how radio interferometer record data and how we save our data. And, you know, I've received so many requests from data scientists who want to join the field, who always try to ask me, how the instrument even measure the data, and, you know, all those type of questions, which is quite very important. If you want to work in the field, you must understand the data, where it's coming from, and so on, and that, yeah. So, well, let me try to put this full screen. Good. Can everyone see my screen?
Okay. Yes. Good.
So, well, a radio interferometer basically is an assembly of a radio telescope connected together that are observed in the sky. So mostly people who are working in this field, they are radio astronomers, they are astrophysicists, they are data scientists, they are computer scientists, they are mathematicians, they are engineer, electrical, and so on. So in this field, we have a lot of varied skill that can work into the field. Myself, I'm not an astronomer, I'm a mathematician and a computer scientist, so yeah. So, well, if you look at the image here, I will just try to give an overview of what is radio interferometer and how the instrument records data from the sky and so on. So if you look at this, please don't be scared about the mathematics. It's quite just the Fourier transform. So if you look at this image, I'm not sure what is happening with my screen. So if you look at this image here, if you are able to see my pointer, you have two antennas there. They are pointing somewhere, somewhere in the sky that I call T. So this is the object that this instrument here is trying to look at it. So basically this instrument measures the Fourier transform of the sky. So it measures the Fourier transform of what he's trying to see. So it doesn't measure exactly what he's trying to look at, but the Fourier transform of that object in the sky. So that Fourier transform basically is our data, okay? So yes, I'll try to, you know, before I come into the big data aspect of this, so I'll try to bring this theory of Fourier transform, which is the instrument, everything is based on this theory. You know, this theory says that a well-behaved signal, as you can see a signal here, can be decomposed into a sinusoidal function, right? So if you take this signal can be decomposed into this type of sinusoidal function. If you can see this function, they are different in resolution, amplitude, and beating. So, you know, if you want to reconstruct the signal, then you must, you know, sum all the signal, and then you have an approximate of this signal. So this is how a radio interferometer tries to behave, as we will see forward. So yes, so here, for example, we have two antennas. You are looking at an object. I just put this smiley, that is the object that you are trying to look. So this instrument will measure the Fourier transform of this smiley, for example. Okay, so for just two antennas like this, you will note that this instrument will just measure a sine wave or a cosine wave. You know, a sine wave, you have positive beating, negative beating, positive beating, negative, and positive. So if you look at it further, you try to increase the size, you know, try to put these two objects in a very large distance. If you look at the two antennas that are very close together, but now if you put them a bit far away from each other, you realize that the beating of the constructive and destructive signal is different. You know, the resolution is quite high now here. But as you can see here, if you compare these two, you see the beating is, the resolution is very low here. And here you see we have very high resolution cosine and sine. So if you try now, if you look at this, we just put this horizontally. If you put this like the two antennas in a different, like you put one maybe let's say you put one of the antenna maybe in the northern hemisphere and one in the south hemisphere, you see this type of constructive signal, right? So the main point is that we just want that is our object should be at least on the positive lobe of the sine, right? So basically now let's assume that the object that we are looking is a very, very large object. You realize that, well, if it's a very, very large object, I increase the size of our smiley, you realize that, well, because our main point is that we want that our object should be light in this constructive part of the signal. But if the object is very light, you realize that part of the object will be the destructive, another one on the constructive. It's very important as we will see further. So if you try to increase again the size of the antenna with that very big object, you see that, well, you just measure part of the smiley here, there, and there. Everything here in the destructive, you don't see them. Good. Similar, this is just the same thing here. So now, as we see, we said, well, for just two antennas, as I showed earlier, just two antennas, you measure a sine wave. This is the sine wave. Two antennas basically is two data points that you will measure. That's why you are seeing these are the data point that you measure. It's not the two antenna on itself, but it's the two antennas at a given time you measure two data points. Okay, so if you increase the number of antennas, you realize that, well, if you look at the image that you are measuring, you are not measuring directly the object, but you have all this, the object that you are looking is just a point. It's just a point, as I said, the smiley, but here you just have a lot of points. So nothing indicates where the object that you are looking. You can't say where the object that you are looking, you can't say exactly the precise position of what you are looking here in this image. So 3 antennas is not enough to do what you want. So if you try to go forward 4 antennas, you see that, well, if you try to compare the 2 images from 3 antennas to 4 antennas, you realize that, well, most of the positive point, we have a lot of positive points here, they will disappear. And you start focusing on the center here. But still, for 4 antenna, you can see this might be the smiley that you are looking, this might be the smiley, and this and that. So you still don't have enough control to say anything here in this image. So if you go to 5 antenna, you see now, you keep reducing the number of peaks that you are seeing. Now we just have some few peaks. So if you go forward 6 antenna, let me just go 7 antennas, you see now we have 1 main peak there in the middle, which is quite brighter than the other peaks. So yeah, you can try to say, well, what you were looking at is this, but still not because you still have some high peaks there and so on. So the main point is here to eliminate all those peaks. So to eliminate all those peaks, you need to add a lot of antennas. For example, 7 antennas just for 10 minutes. you look at the data, we have this type of, we have the number of, if you want to count the number of points, 10 minutes, the number of points will increase. The quality of your image is also very good. If you move to 1 hour, now look at 1 hour. If you compare the number of data points between 10 minutes and 1 hour, see that in 1 hour, we have a lot of data. Then our image now is quite very good. So the main points here, 8 hours, we have a lot of data, and now we can observe, you can see, you can identify the position of our smiley, but well, in this case, this is just the response of the instrument toward the smiley, which is this. This is the response. The response is very, very good, right? So if you really want, if you look at this image, you see that you have all this sort of noise in the background of this point and all this stuff. If you want to remove all those stuff, you need to increase the number of antenna, increase the observing time from 8 hours to 12 hours, 24 hours, 2 days, and so on and so on. So by doing all those things, you keep increasing your data size, the data volume that you are recording. Yeah, so as I said, from my the previous slide, this is how our database looks like. So baseline here means that is the distance between the two antennas. So these are the number of, well, the baseline, the number of antennas will determine the number of baseline. For example, if you look at this math expression, NA is the number of antennas, and this expression is the number of baseline. So this number, the number of antennas will determine this number. So basically you have a lot of baseline as the number of antennas increases. Then this is now the bandwidth. We are here in the signal processing domain where we have to observe within a given frequency range bandwidth. So this is the bandwidth, so we have the number of antenna, number of bandwidth for each point, for each frequency in the bandwidth and each baseline, you have a sort of frequency range and time range. For each of these point frequency range and time range, you have a sort of data that you measure, which is a 4x4, well, which is a 2x2 matrix, right? So if you look at, we look at this equation very closely, you realize that, well, the data size, as I try to express here, if I suppose that, well, one data point is represented in our computer memory into 32 bytes, this is the number of antenna, you realize that, well, this data size is a factor of the number of antenna. So if the number of antenna increases, the data size also increased. So this is the number of subband. In this representation, we just have one subband. So we have this subband like this, many in our database. So you see that the number of subband also is a factor of data size, increase the data size. So the observing time, this, you realize that, well, if you look at this, the number of time, as the observing time increases, you also increase your data. Same with the bandwidth, which is this. So, well, I will come to the point with the SKA. The SKA basically is the world's most sensitive radio telescope, which is under construction in South Africa and in Australia. So currently, well, people are still working on the SKA1, which is the SKA MITS in South Africa. And if you look at the SKA1 MITS under construction in South Africa, you have this number of antennas, dishes, right? 197 dishes, okay? So if you just look at this, for just 0.1 second observation time, you see previously that, well, our data increases as the observing time increased. So yeah, if you just want to use the SKA, the prediction says, if you just want to use the SKA during 0.1 second to look at the sky, using just 0.1 megahertz as bandwidth, okay, you will record 142 terabytes of data. That's a lot. So it basically means that if we want to observe during, just imagine yourself, project yourself, like we want to use this type of instrument to measure data during 2 days. Just imagine what you will have. For 0.1 second, you are already in order of terabyte. In 2 days, what will happen? 3 days, and so on. So if you look at the low frequency, the part of the SK under construction is in Australia, it will have this number of antenna quite a lot. So the same thing, 0.1 second, 0.1 megahertz, you'll be at this regime, 157 terabyte. Oh, this is 157 terabyte per second. Imagine that these two instruments, if we have to combine these two instruments together and do a simulation, and this will do an observation, and this observation will take, let's say, for a day or 2 days. We all agree that, well, we won't be able to record the data that we want. So, you know, there are a lot of challenges. It comes from this. So, yeah, so as you see, the challenges of the SKA, you know, I also want to remind the panel that the SKA is not just, it's a great tool for research and for engineering, and not just for astrophysics or astronomy, but, you know, computer scientists, they have their part to play in, mathematicians, they have their part to play in, and engineer. Same thing with data scientists, machine learning. So basically, our work here at Rhodes, you know, I'm working under the Radio Astronomy Center of GRAT, Radio Astronomy Technology and Techniques Center at Rhodes University. At the same time, I'm lecturing under the Department of Mathematics, where we have a machine learning group. You know, we have a lot of students who are working on things like this. So myself, I've worked a lot on compression algorithm, this data, how to compress this data, you know, the data and the model also. If, for example, you build, for example, a model, let's say that is classifying radio galaxies, for example, and, you know, because the data is quite very big, and we can't, I mean, the computational support is quite limited to record this type of data. Maybe in the field, you need to do a sort of model compression in such a way that, you know, low device instruments, maybe very computers which are not quite very high in capacity can run this model. So we need things like that, you know, and automatic processing also of the data, you know, so people are doing transient detections. These transients are sources in the sky that varies in times. So people are using machine learning to detect this. Our here at Rhodes, we are using classification algorithms, supervised algorithms to do classification, classify radio galaxies and so on. We are also doing data segmentation because the image is very large of a radio telescope, and this image contains a lot of sources. So basically, you know, the time that an astronomer will take to, you know, segment all these sources before classifying them and so on is quite huge. So here we are using deep learning techniques, for example, units to do this type of segmentation and so on. Also radio frequency interference detections. Radio frequency interference are, well, they are any type of unwanted signal that can contaminate the data where the telescope is located, for example, our cell phone and so on. So we need machine learning tools to, you know, try to detect all those things. Another main challenge here is the imaging and the reconstruction. As you saw previously, well, what the instrument measure is not directly the image of the sky, but the Fourier transform of the image of the sky. So, you know, and, you know, because we are in practice, it means that, well, all these things are sampled, they are sampled, and they are not a continuous signal. You have to sample all these things. You know, we are using computers they are band limited and all this stuff. So this will introduce a lot of distortions in the data and so on and so on. So we need a lot of techniques to, you know, image this data and reconstruct the sky. So the presentation today will be mostly based on this third aspect, the imaging and the reconstruction algorithm, you know. So to give a very brief overview of the image, so keep in mind that the image that the instrument measure basically is the true sky. The true sky is what the instrument is looking at, convolved with the instrument response, right? As you can see, the mathematics, the convolution. Okay, so you see here, let's assume that we are looking at 4 objects in the sky. In this case, they are very close together, right? So these 4 objects, this image that we are looking is the image that we obtained from our telescope. But this image basically is not clean, it's still dirty. It has a lot of components that I'm going to explain later in there. For example, the instrument response. So if you look at all those round lobes around all those bright points, are the response of the instrument toward the sky. Okay, so basically this image is the convolution of the true sky with that response. But we are looking at the true sky. So we try to remove that convolution by doing the convolution, right? Which is the opposite of convolution. Okay, so basically if you know that response is your filter. So if you know that response, then you can go toward the convolution directly and remove it. Okay, so but what we know, okay, before I go toward a bit deeper, let me go to this. For example, this is an image that I did from the current work. So every stuff that you are seeing here, it's some object in the sky that I'm not aware of this as a data scientist, but an astronomer will tell you all these objects. We try to identify and classify them. Myself, I don't know. My problem is just to make very beautiful images for them. So if you look at this, assume that this is the center of your image, then you realize that at the center of the image, the response generally is quite high at the center. And you won't see any distortion. Look at all these sources here, those objects, they are distorted in shape. This is not how the true object looks like in the sky. This is caused by things that I said. For example, during the convolutions, during the measurement, there are convolutions and averaging and so on that we keep doing when we are doing, we are trying to clean an image. For example, in ConvNet, you do a lot of convolutions and convolution and try to, when you do the convolution, you do averaging and so on and so on and so on. So basically this image, those are things that happened that I don't want to go toward very deep in that. I just want to show you here that, well, all these objects in real life, they are not distorted as you can see. So if you look at the right image, it is the correction that I did, but is the correction that I did. So to do this type of correction, you must come at each source here and compute the convolutional filter at that point. Those convolutional filters are at each point, they are quite different. They are different. So you have to compute all those things. Okay, I'll come back to what in that later on this talk. So yeah, we saw that, well, the sky, the image that the radio telescope measure is basically the true image convolved with the response of the instrument. That's just the math of convolution. This for me just means convolution. It's just the same representation as this. It means convolution. Yes, so if you want to look at convolution in terms of direction-dependent pixels, you can write it like this. All of us, we know this. This convolve that. This is the filter. This is our data. You can express it as this. Where our filter now is a function of pixels, right, across the sky. So in interferometry, what I want to remind you here in this field is that they know in this filter that we are seeing, they know very well just the filter at L0 is equal to 0. So this is well known. The response of the instrument is well known. And that response is very high at the center of the image you saw. So I'll go back to this image. For example, this image, so that response, is the response. It's somewhere here, like this very small image. This is the response. That's the filter at each point. But keep in mind that this image is quite, I mean, it's a very small field image that you see that the response doesn't vary that much. But if you look at wide field imaging, you know, the objective is to do very wide field images, observe the sky in a very large range. You see that that response will start varying as you move toward that center. So yeah, you know, if you want to correct those sources, as you saw in the previous image, you have to evaluate all this. For each L0, you have to evaluate this component. It's quite very, very computational challenging, as I will show it later. So basically in the field, they have the habit to just use what they know. They just, because the computational is very, very high, no one wants to attempt to compute all this response at each pixel in the sky before trying to correct those morphology distortion that you saw. So they will just use like this as an approximation, which is not good, right? Because of which is not good, but they are forced to do this because of the big data nature. No one wants to be computing all these things and it will take forever. So basically this worked well. We said, okay, it is true that all these convolutional filters, they are different in the image around everywhere. How can we, you know, not compute all these things directly, all these filters directly? How can we do a sort of approximation just based on what is known, as I show you here? Based on this, how can we compute all these filters? Okay, good. So to do this, we try to understand first the behavior, where the distortion is coming from. So we try to do a sort of modeling, you know, evaluate the convergence and all this stuff and all stuff. I won't go into the math a lot, you know, so just forget about that math. So in this slide, we said, well, let's assume that we are looking at an object, which is this object, which is a data function. For those who did sampling, signal processing, it is just a data function. So we said, well, if we are looking at that one object, because the instrument measures the Fourier transform of something that is looking, then this is our data that we will have. That's how we model that. Then, well, we said, well, because we are not in the real world, you know, everything must be discretized. We say, okay, let's discretize now the data. Still using a data function for the discretization, the sampling. We sample the data. Then we said, well, generally, you know, all the convolution happens, convolution plus averaging, you know, and so on. Well, the pooling that we use is averaging and so on. So, you know, and then we're like, okay, cool, we have a convolution. We find a filter, which is that, we present that by that, then we try to do a convolution with our data, which is that, you know, and then we try to do averaging. You know, when we do the convolution, we do averaging at different positions in the sky. So our pooling here is averaging. So, you know, averaging can be represented as this, that summation, that's averaging. So at the end, you know, this is what the instrument will measure, which is your filter, convolve the data. Okay, and then, you know, we try to like, okay, because I won't go to it in the maths, you know, we try to understand this, and we found out that, well, this is the factor that came with the distortion. You know, the distortion comes with a different filter that we are using for the convolution, which is this. The X is our filter. Okay, so, well, then we try to image that, you know, we compute that, and you can see that for different L0, you know, for different L0, we have different distortion. Here we have like very small distortion. You see here we have very large distortion. This is our filters. Then, you know, we said, well, how can we approximate this based on just what we know? So we know the filter, which is the response of the instrument. We know that. We said, well, let's try to build a function that will describe the distortion effect around each position in the image, each pixel in the image, knowing the pixel at the center of the image. So this is what we bring the distortion. I did not go into it, how we did this. This is just a physical representation and so on. So we model this distortion, then, you know, for each pixel, we just multiply by what is known. And then we have the distortion, the filter, the convolutional filter at each pixel in the image. So if you want to look at it very well, you know, I'll go with that. So this is what is known at the center, and we are looking at the filter at a given position in the image. So this is basically our distortion function. This is the distortion function that I was saying. If you multiply these two, then you have that. And then you have this filter at that exact given position that we are looking for. This happens to be computationally very, very cheap. As you see here, for example, if you look at this expression, if someone wants to keep computing all these convolutional filter around the sky everywhere, this is the complexity of your algorithm. What will happen? You know, this expression comes from the fast Fourier transform, for those who have used the fast Fourier transform, and which is the Fourier transform. And, you know, this expression is the number of data that you have. We know that this number of data is quite very, very big. And this is the number of pixels in your image. It is also for wide field imaging, it's quite very, very big. For someone who is doing, generally this is very big, and this quantity is bigger than this. So if you just assume that this quantity is equal to this, then you have like number of pixels square log number of pixels, which is quite huge in computation. That's the very, very small case that you can have where this is equal to that. But this is quite very high than that exponentially. So no one wants to go for something like this. But with our approximations, well, you know, the computational complexity we scale as you are seeing. This is the computational complexity to evaluate the filter at the center, what is known. This is what, no matter what everyone will do, this is what has been happening. They always do this computation. And then the complexity comes with the computation of our correction function, which is quite very cheaper because, you know, this is just quite a constant. It's quite very cheap. You know, this function, it doesn't involve data. It just involves a sort of sign function, that's all. It doesn't involve the data that we are measuring. As you can see, it's not a function of data. So it's quite very cheap. Yes, so now we try to look at, compare our result with what is currently, what we have in the literature currently. So currently, well, as I said, all this convolutional filter is approximated with the response of the instrument towards the center of our image, right? So if you are using that, this is that the true, if you want to compute this directly, that's the true convolutional filter, and this is the response at the face, what is known. So, well, we just try to find the difference, as you can see, and put this in the decibel space and transform it into percentage. So this is the factor. You see that at a position 0.5, well, this is measured in degree. Astronomer measure the position in degree, but I want you to look at this like this is a position of a pixel, which is very close to the phase center, where there is no distortion. You see that you just have an error of 1.14. But if you go toward, you want to, for a very large image, you go far from this 0.00, you see that you are having an error factor of 36.14, which is quite very high. Then with our methods, you know, we look at, well, the distortion maybe at a given position, let's say very close to what is known, 0.5. You see that, well, the red is the approximation of a filter and the blue is the exact. So if you measure the difference between that, there's a difference in decibel space. You see it's quite below minus 20 decibel, which is quite very good. And also, if you want to compare with what currently is being used in the literature, at 0.5 degree, you know, look, the error is 0.1%. Why with current methods, at 0.5 degree, the error is 1.14, which is high. 1.14 is quite higher than 0.1. You know, and at the same time, I want to emphasize about this is that because we are in the wide field, very large images, you know, we want very large images. So for a very large image, you see the error is 1.5. Why, if you want to do this type of large image using the current method, you know, 2.5, the error will be about 21%. Why using our approximation, you have just 1.5%. Good, so yeah, it's just the same interpretation with this. Yeah, so I think I'm at the end of these presentations, and if I did not go through the technical aspect and, you know, a lot of, I mean, this is quite signal processing stuff. If you are interested, you can, there's a paper on this accepted, you can look at this, that's the link on archive, yeah. Yeah, so most of the presentation most of the slides in my presentation, I took this from this quite very well-known researcher in the field and different sources, yeah. Thank you, I will stop here. If there's any question, please.
Thank you, Marcel.
Yeah, welcome. Thank you so much.
Yeah, I think while we're waiting for any questions, if there are any questions, we will just open up in a second or so. For me, in this case, it's a very interesting, especially when you're going into now, yes, there's a lot of signal processing that has to happen on one side to deal with like the amount of data that you need to go through to find signals. But at the moment, where do you see kind of the promising next steps in this space?
Yes, so the next step here is, you know, is to use this to do the deconvolution for the astronomer, to implement now the algorithm, the exact algorithm for deconvolution, right? To clean up, to use it and clean the image. Okay. So that's the next step now for this work. Yeah. Yeah, I think so. And also for this work, for someone who is looking at deep neural network, you know, where we keep using filter and then we have our future mapped, you know, at some point we want to do the deconvolution. But to do deconvolution, you must know all the convolutional filter that you use to do all that convolution. Okay. So imagine yourself that you are at the regime where you don't know all those filters. Yeah. And basically, generally, we don't know all those filters. Sure. It's those who are using TensorFlow and all this stuff, you don't know. But from the with this method, from the feature map, you can approximate. You can estimate all those filters so that you can use for your deconvolution. Okay.
I guess another one then maybe connected to that is, how do you see, what's this? If now there was a different map, so knowing what's actually around there, do you think we could actually train an architecture in a deep net that then can actually do that internally to actually identify these? Okay.
Yeah, with the different maps, yeah, because with it, what we have to do is to compute. Well, we have to know at least one of the filter and where the filter was used to convolve the data. Okay. We just need one filter. So if we are able to know one filter, and then we can estimate all of them.
All right.
Yeah, I think this is quite a very theoretical, and I'm quite, yeah, when I was preparing this, I tried to, you know, take it really, really like if very down such a way that everyone can pick it up, because there are a lot of maths behind and the signal processing aspect and so on. Yeah.
No, thank you. If anybody has a question, you can unmute yourself and then ask your question.
Hello. My name is Ulrich, so I'm kind of the most familiar with this because I'm also part of a radio astronomy group. So actually my question was kind of, all this derivation, is it kind of general purpose for any radio telescope, or was it specific to the kind of telescope you use for your simulation? Or will the method just work for any kind of array? I'm talking about the correction factor.
Oh, thank you very much. And the correction factor, obviously, it will be different for each telescope, because for each interferometer, each telescope, the resolution of the image is different, and the sensitivity of that instrument is also different, and also the number of antennas are different, because, for example, if you want to take a very small telescope, then you don't need things like this for a very small telescope, because the data is very few. So you don't need this type of approximation. You can compute this directly. But, you know, this will work very well to answer your question for quite very large instruments, like the SK, like Meerkat, you know, yeah.
Yeah, okay.
Okay.
Because I imagine something like maybe probably the SK or the VLBI, which has very long baseline, should kind of be, should have more difficulties with the wide field imaging and compared to a more compact telescope.
Exactly. Yeah, this will be also quite very good for what you mentioned, the VLBI, and so on. Yeah.
All right. Okay. Any other questions from?
Just a final question.
Yes.
So in terms of you've talked about the computation, but then in terms of memory, does it in terms of memory in implementing the algorithm, is it is it expensive, because now you kind of have two PSF to store in the memory, the correction factor and the normal PSF?
Yeah, that's a very good question. In terms of the memory usage, like as you see from the computational complexity, as you saw, we don't have to store all the distortion, the distortion factor for each pixel. You don't have to store it. You can just compute it and apply it directly to the pixel and move forward without storing this. You know what I mean? Because obviously, if you want to store it, then it's going to be memory quite intensive.
Okay.
Yeah. Thank you so much.
Okay. Thank you. Mandla, you had a question?
Yes, my name is Mandla. Like, I have a question. You mentioned something related to, as a person who's coming from the computer science space, I would like you, maybe can you just mention like the top 3 challenges that you faced while working on that part?
Please, can you ask the question again?
I'm asking like what were the top 3 challenges that you faced while working on compression algorithm?
Yeah. So you want me to name some few work that we have done in the compression research work, or
More
the
challenges that you faced, yeah.
Oh yeah, so basically that's quite interesting, right? So basically what we are doing the compression is not lossless compression.
Yes, the challenges.
Yes, so it's not lossless compression. You know, with lossless compression, you compressed, like, you know, you compress, and then when you want to use, you have to uncompress, and then it will recover back the space, right? So we do lossy compression. You have to compress it and then use the compression version, right? So lossy compression, obviously, the drawback on this is that you throw away a bit of the information that is in the data, but you know, when you are doing the compression, you must make sure that, well, there's a trade-off between the signal and the compression factor, right? So that's the challenges in the compressions, because we want to compress without losing information, but we want to compress the data. So you must find a balance between losing some information and your compression factor ratio. That's the main challenges that any algorithm compression that you are looking, we try to do. Am I clear, Mandla?
Yes, thank you. I did get your part.
Yeah, thanks.
Okay, Samuel, do you want to ask your question?
All right. So thank you, Marcel, for presenting this. I've been wondering, knowing that your data set is very huge, can you give us some of the details on the type of compute resource you use to train like your models? Yeah, so
Samuel, can you speak a bit louder? I can't really hear you.
Oh, sorry about that. I'm having a bit of cold here.
Oh, okay.
So, knowing that your data set is very huge, I just want to find out the type of computer resource that you use. Like, do you have like a kind of big supercomputer that you use for training all these things?
Thank you very much, Samuel. Yeah, it is true. We don't use our own personal laptop. We use our laptop just like an interface. So we have quite big computers provided by Rhodes University, and some at the SKA South Africa that we used. So if you want to do this type of work with your own computer, then it will take forever. You can't even do research. Yeah, myself, my laptop is quite someone will look at it and like, oh no, it's quite, it's a big computer and so on. But my laptop cannot do the work that I'm doing without using all the supercomputers. Yeah, so we have all those equipment at the SKA level and here at Rhodes.
All right, thank you.
Okay, thank you. Any other questions? Okay. Doesn't seem to be any more questions at the moment. Thanks, Marcel, for taking this time in this morning. I think it's an interesting area. I think also, especially maybe for people to get the, oh, sorry, since my video's off, this appreciation, especially of like, you know, signal processing is an important thing. I have a background in electrical engineering. So
Okay.
one of those things that you do kind of come across. For me, that's where, especially convolutions, the first time I got in kind of exposed to them were there. My own personal like, you know, light bulb moment mostly came when I started dealing with image processing with convolutions, where now it made sense from the side of the, like, you know, image of the signal processing. But now, yes, we have kind of this now building these large networks that are building on actually signal processing fundamentals on there, and then we actually then end up seeing it in how we can actually use it to extract useful information from things like radio astronomy. So this is very interesting, and yeah, we look forward to seeing what comes out of Rhodes over the next few years. Thanks everybody for joining in this morning, and I want to thank also Marcel again for coming through. You have a good day. The recording of this will probably be available sometime in the afternoon when you go to our research group website. It will be under the news section. So thank you again.
Thank you very much, Percy.